It's weird, but at the same time amazing, that all innovations in our world nowadays can be traced back to simple mathematical equations. Knowing what will happen to a car when it hits a wall or a post traces back to partial differential equations. AI can be traced back to trees and graphs, so on and so forth. That is how mathematics affect technology, and it's still being improved on as we speak. Automata theory is also the foundation of some of these technologies, and it too relies on the fundamentals of mathematics. As students that focuses on computer science and information technology, it's important to us to have a grasp on how these fundamental mathematics work. So, as they say, why not go back to basics? Welcome to another installment of Automata Theory and Formal Languages, where today we'll tackle the basics on where automata was based on. This is Mathematical Preliminaries and Notations. If you're new here, welcome, but you may want to check out the first video tackling about the introduction of automata theory and formal languages. The link is in the video description. Now let's move on to our discussion for today, and that is mathematical preliminaries and notation. But before anything else, let's go ahead and have a recap on what we have discussed last meeting. So last meeting, we have introduced you to automata theory and formal languages, and the introduction taught us about the theory of computation. So there are three things in the theory of computation, but our main focus is to create a computer that can accept an input, just like this one, process it or think about that input, and create an answer, whether it's yes or no. So this is just about a typical computer. We also talked about the automata theory, and of course, the classes of automata and its layers. So automata has 6 layers, starting with combinational logic, then we have finite state machine, context-free languages, push-down automata, Turing machine, and of course, undecidable. Now let's go ahead and discuss why do we have to tackle mathematical preliminaries and notation. So again, this is just a review of the main ideas in mathematics that will be our guide and conclusion we draw while studying automata theory. Because just as I mentioned in our introduction, this is the very foundation of automata theory, just like anything else. That's why we need to review this just in case you forgot some of them. Students will need a reasonably good grasp of the terminologies and of the elementary result of set theory, functions, relations, and an understanding of mathematical reasoning. So most of our topics that we'll tackle later on in this series will be all about sets, functions, and relations and other things when it comes to math. Trees and graphs will also be used frequently, especially directed graph that shows how machines process states. So trees and graphs will be prominent when we're discussing finite state machines and others. That's why you need to remember what is the difference between trees and graphs. So let's go ahead and discuss what are sets. So a set is a collection of distinct elements. So those distinct elements could be finite or infinite without any structure other than membership. This means that the order of the elements does not matter. So let's discuss first how a finite set works. So a set can be specified in a finite manner by enclosing some description of its elements in curly brackets. For example, the set of integers 0, 1, 2, and 3 is shown as this. So set is equals to curly bracket 0, 1, 2, 3. We can also rearrange these numbers if you want to, just like this. So it can be 3, 1, 0, 2. Because again, the order of the elements does not matter. As long as all said numbers are inside the set, it is still called a set. So what if we have a lot of numbers that is in a consecutive manner? Let's say for example, we want numbers from 0 to 100, or we want all the alphabets from A to Z, but we don't want to write everything down. That is where we use ellipses. So ellipses are used to signify there are other elements in the set, but instead used to write all down. For example, a set of all the lowercase letters of the English alphabet is like this. So if we want to show that the set has all the letters of the alphabet in lowercase, we use this 3 dots right here. So that means letters C, D, E, and other letters are also included inside this set. Now that we know how to use a set in a finite manner, How about if we want to use it to signify infinite numbers? A set can be specified in an infinite manner using ellipsis as the last element in the set. Let's say, for example, we want a set of all positive even integers. In order for us to write it down, we will use this. So this means that the set has infinite even numbers inside because, as we can see, 2, 4, and 6 are even numbers. Then we added the ellipses right here. That means all the positive even numbers are also included here, including millions, billions, and whatnot. We can also use an explicit notation for this example. We want a set of all positive even integers, so we can also use a rule like this. We will use I as our variable. It says here that I is more than 0 and I is even. So that means all the numbers inside this are positive because I is more than 0, and all the numbers are also even because the rule says here that I is even. Because we read this as a set of all positive integers, how do we read this one instead? So this is read as S is the set of all I such that I is greater than 0 and I is even. So it's just like programming as well, wherein we put in the rules whether the number is even or not. There are certain rules when it comes to our set. So if we have duplicate elements inside the curly brackets, it cannot be considered as a set. So let's say, for example, this one, which is 1, 1, 2. We cannot consider this as a set because 1 is repeated. So for us to indicate that X is an element of the set S, we write it like this. So we will be using this symbol right here. This symbol means an element of. So how do we write this down on, let's say, for example, a number? So for example, 2 is an element of the set 0, 1, 2, 3. So we write it like this. 2 is an element of the set 0, 1, 2, and 3. How about if we want to indicate that a certain variable is not an element of a set? We also have a symbol like this. So what we'll do is cancel element of to signify that it's not an element of the set. So X is not an element of the set. Let's say, for example, 8 is not an element of the set 0, 1, 2, and 3. We write it like this. So 8 is not an element of set 0, 1, 2, and 3. How about if we want to signify that the set is empty or null? We also have an empty set or null set, and it is indicated by this symbol. This means empty or null. When it comes to empty set or null sets, we don't have to put it in a curly bracket because again, it is empty. Now let's move on. We also have what we call subsets. And the subset is a set where every element are also seen on another set. For example, we have set 1 and set 2. And let's say, for example, that S2 has all of the contents of S1. That means S1 is a subset of S2. So we can write it like this. This symbol means a subset of. So S1 is a subset of S2. So let's say, for example, the set 2 is a subset of set 0, 1, 2, 3. So that means this set is also seen on the set, which is right here. So there are also common mistakes when using subset of and element of. Take note that do not use subset to denote an element. Sets or subsets must always be enclosed in curly brackets. So what do we mean by that? So you may use it like this. So 2 is a subset of 0, 1, 2, and 3, which is fine, but it's not inside curly brackets. That's why this is not a set. Rather, it is an element. So what is the right way of using element of and subset of? It should be like this. As mentioned, set or subsets are inside curly brackets like this, and elements are not inside curly brackets like this. Simple enough, right? Let's move on. Now, the size of a set is denoted by these symbols. These symbols means absolute value. So this means give the number of elements inside a set. So let's say, for example, the absolute value of the set 0, 1, 2, and 3 is equals to 4. That means the number of elements inside this set is 4. So what if our set is actually infinite? Let's say, for example, the absolute value of the set I, wherein I is even, so that will be infinite as well. And we also have what we call power set. A power set is denoted by 2 raised to s, which means a set of all subsets of s. This means all the possible subsets of a set is inside another set, just like this. For example, our set is 1, 2, and 3. The power set of set 1, 2, and 3 is equals to this. All the possible sets inside set 1, 2, and 3 are empty set of 1, set of 2, set of 3, set of 1 and 2, set of 1 and 3, set of 2 and 3, and set of 1, 2, and 3. Because again, you can have a subset that has the similar numbers. What about if we have a set of 4 and 5? So the power set of set 4 and 5 are empty set of 4, set of 5, and set of 4 and 5. So those are the things that you have to consider when it comes to set. Now let's go ahead and discuss set operations. So there are 4 basic operations in a set, and they are union, intersection, difference, and complementation. Let's start off with the basic one, which is union. So union is denoted as set 1 union set 2. So this is the symbol for union, which means all elements from set 1 and set 2. For example, we want to know the union of set 0 and set 1 and 2. All you have to do is to combine the contents of these two for us to have the union of these two sets. So their union set is 0, 1, and 2. How about two sets that has the same numbers as well? Just like this. So we have set 0, 1, and 3 and set 1, 2, and 3. So if we try to get their union, we will combine the same numbers as well. So the union of set 0, 1, 3 and set 1, 2, 3 is equals to 0, 1, 2, 3. Because both of the set have number 1, which is right here, and number 3, which is right here. How about if we try to get the union of two infinite sets? Let's say, for example, we have this set wherein all the numbers here is even and all the numbers here is odd. We can just write it like this: 1, 2, 3, 4, then ellipses, meaning all the numbers that are possible or infinite. We can also write it like this. So we try to union all the numbers inside these two sets. All we have to do is to remove the rules I is even and I is odd. We will also get the exact answer, which is all the numbers that are positive. The next set operation is intersection, and it is denoted by this symbol. So set 1 intersects set 2, which means elements that are in both sets. For example, we want to intersect set 0, 1, and 2 and set 1, 2, and 3. What will be the answer? Obviously, this set has 1 and 2, and also this set has 1 and 2. So the intersection for these two sets is 1 and 2. How about this? This set has 1 and 3, and this set has 1 and 3 as well, so their intersection is 1 and 3. How about infinite sets, just like this? If we try to intersect all the numbers that is even and all the numbers that is odd, we will get an empty set because they don't have similar numbers inside them. Our next operation is what we call complementation of a set. So it is denoted by a bar on top of the set, which means all elements that are not in S. So how do we get the complementation of a set if we're trying to get all the elements that are not inside the set? We often consider a fixed universal set of all possible values, also known as the universe. So U means universal set. So what are these universal sets? So examples of these are sets of all integer numbers, set of all computer programs, set of all possible grades for the course, so on and so forth. So if we're trying to get the complementation of a set, we must first define what is the universal set or the universe itself. For a set to be a subset of the universe, the complementation of the set must include all the elements of the universe that are not in the set. So let's say, for example, the universal set is a set of all final grades from 0 to 100. So what can be the possible set for this? So let's say, for example, that we want to get all the grades that is more than 50, and we'll call this set the passing grades. So X, wherein X is more than or equal to 50, so this will be our set. So if our set will only consist of numbers 50 and higher, what will be the complement of this set? Obviously, that will be 49 and lower. So what we'll write down is the complement of the set is equals to x, where x is less than 50. And we'll call that set the failing grades. So that is the complementation of a set. And again, that means all elements that is not in our set. Aside from the 4 basic set operations, we also have another, which is the Cartesian product, and this is a list of all possible pairs with the first element from set 1 and the second element from S2. So if you're familiar with the FOIL method, wherein you multiply the first number to the first number of the next, so on and so forth, that is what we're doing with the Cartesian product. Let's have an example. The Cartesian product of set 1 and 2 and set A and B is as follows. What we're going to do is combine 1 and A, so that's 1A, and then 1 and B, so we have 1B right here. Then we'll combine 2 and A, that's why we have 2A here, and 2 and B to get 2B. So that is the simplest Cartesian product example. Let's make it a little harder. Let's make it 3 this time. The other one is number 3 on set 1. We still have A and B right here. So it's almost the same. Then we'll add 3 and A and 3 and B right here. How about we make it a little harder? Instead of 2 sets, we have 3. So it's basically just the same. Get the first ones. So that's 1AX, 1AX, 1AY, 1AY. Then we'll go to B. So that's 1BX, 1BX, 1BY, 1BY. Then let's go to number 2. And the same thing as well. And again, this is the Cartesian product, and it is a list of all possible pairs within the first element from set 1 and the second element from set 2. Before we end set operations, let's discuss one important thing that we have to mention, and that is the De Morgan's law. So if you're familiar with our subject before, which is digital logic design, we already discussed what is De Morgan's law, and the same thing is actually right here in a set. So the first rule in the De Morgan's law is this. So the complement of set 1 union set 2 is actually equal to the complement of set 1 intersect the complement of set 2. Because the complement of union is intersect. So instead of complementing union itself, just use intersect. The same thing can be done like this. So the complement of set 1 intersect S2 is equals to the complement of set 1 union the complement of set 2. Because again, the complement of intersect is union. So those are the De Morgan's law. Now let's move on to functions. So what is a function? A function is a rule that assigns to elements of one set a unique element of another set. So we'll be using 2 sets right here, and it is written like this. So f here denotes a function. Set 1 is called the domain of f, and set 2 is the range of f. So if the domain of f uses all the elements inside of set 1, that is called the total function on S1. Hence, it is called partial function. So what do we mean by that? Let's say, for example, we have 2 sets right here. So the set 1 is 1, 2, 3, 4, and set 2 is A, B, C, D. So let's write it like this. So as mentioned, set 1 is the domain and set 2 is the range. And let's say, for example, that the function uses all the numbers inside the domain, but only uses some numbers inside the range. That is still called the total function because again, the function used all of the numbers inside the set. What if, for example, the function uses only 3 of the elements inside set 1? So that is what we call the partial function. It doesn't matter how many elements inside the range is used by the function. As long as the function uses all the numbers, it is called the total function. And if not, it's called a partial function. Let's move on to relations. So relations are actually functions as well, but it is more general. In a function, each element of the domain has exactly one associated element in the range. Just like as you saw on functions, all the elements inside of set 1 is only used once. But in a relation, there may be several or possibly none. So what do we mean by that? Let's use the examples again. So that's set 1 is 1, 2, 3, 4 and set 2 is A, B, C, D. And let's write it down like this. So before, we have 1, 2, 3, and 4 pointing at A and B only. But in a relation, it can be like this. So what is the difference? As you can see, one of the domains, which is number 1, is pointed twice at the range, which is A and B. So there are two duplicates inside the function, and now we cannot consider it as a function itself, rather it's a relation. It also doesn't matter if we use all the numbers inside the domain or not. There's no partial relation or total relation in this, just relations and nothing else. Now let's talk about equivalence. Equivalence is a special case of relation, and it is usually denoted by this symbol. The symbol 3 equals, that means equivalence. And this must satisfy 3 properties. So we need to satisfy reflexivity, that is x equivalence of x. We need to satisfy symmetry, that is if x is equivalence of y, then y is equivalence of x. And then we need to satisfy transitivity, that is if x is equivalence of y and y is equivalence of z, then x is equivalence of z. So these 3 must satisfy a relation in order to call it equivalence. Now let's move away from sets and let's discuss graphs. You may be familiar with this as you already studied data structures and algorithms. It's also the same, but we'll try to make it simpler. This is a collection of vertices connected by direct edges. Think of it like intersections on the road connected by a one-way street. So the vertices right here is these letters. So that's A, B, C, D, E, and F. And the direct edges that we're talking about is the arrows pointing at each vertices. So A has a direct edge on C, but C doesn't have a direct edge on A. A has a direct edge on D. D has a direct edge on C and E. C has a direct edge on E. E has a direct edge on B. B has a direct edge on F, and F is the only one connected to A. We also have direct edges like this. That means it will go back to itself only. So like this one, A will go back to A again, and B will go back to B again. So let's talk about paths. A path is a traversal or walk from one vertex to another along directed edges when each edge is visited at most once. So the aim here in path is to go from every single vertices from one point to the next. So let's say for example a simple path from A to F. For us to get from A going to F is like this. So we're going from A to D, D to C, C to E, E to B, then B to F. There's no direct path from A to F because as we can see the direct edge is pointing from F to A. And we cannot use A to C right here because we won't be able to get to D. That's why the most efficient way to get from point A to F while traversing all vertices is this way, like this. So if a path visits each vertex at most once, it is called a simple path. Hence, it is not a path. On graphs, we also have cycles, and a cycle is a path from a vertex to itself. Let's consider the example again right here, but this time we're going from A, going back to A again. So the simplest path that we can take to cycle from A is A going here and A again. Because we have a loop right here, so this is the possible way to cycle from A. We can also use the path example that we have earlier, so that's A, D, C, E, B, F. And we can also use the vertices that loops from itself, so that's A, D, C, E, B, B, F, A. So those are the possible cycles in this specific graph. Now let's move on to trees. And again, this was discussed on data structures and algorithms, so we won't be discussing this any further. So a tree is a special case of a graph. So if you're going to look at it, it's actually almost the same as the example before, but this time it is going down, just like this. So the special rules of a tree is as follows. So it has a root vertex and exactly one path from the root to other vertices. Just like this, A has only one path to B, C, D. B cannot go back to A, but it can go to E and F. C can go to G, D can go to H, and H can go to I and J. Trees has also its own relations. So if there's an edge from a vertex down to another, let's say for example, B to E or A to D, the one above is called the parent and the one below is called the child. So let's say for example, B is the parent of E, while E is the child of B. So everyone from the top can be a parent and a child as well. So let's say for example, A is the parent of BCD, BCD is the child of A, but B is also a parent of E and F, C is also a parent of G, and D is also a parent of H. So those are the relationships that we have in trees. So how about the parts of the trees that has no child? That is what we call a leaf. So all the nodes that we can consider as leaves are E, F, G, I, and J because they don't have any child nodes. Let's continue. Now, the following are not considered as trees. So this one will never be considered as a tree because one of the nodes has two different paths. So B and C is the parent of F, which is again impossible on a tree. And this one will never be considered as a tree as well because there is more than one root. So R and H is the root of this, which is again impossible. There can only be one root. And that concludes our lecture for today. If you have questions, you can leave them on the comment section of this video or in our Google Classroom. You can also contact me on my social media accounts right here. And thank you so much for watching this video. Have a great day.